Hey guys, this is Alan with Bothell STEM Coach, and today we are going to be working on another AP Physics 1 circular motion problem. Okay. Um, as usual, I suggest that you pause the video, take a look at the problem, try to do some parts of the problem, and then once you've gotten as far as you can or you've completed it, come back to the video and see how I approach the problem and see if we got the same answer. Now, I don't actually guarantee that I'm 100% right on all of these problems. I'm pretty sure I have most of it right, but I do make some small mistakes sometimes when I do these problems. So a ball attached to a string of length L swings in a horizontal circle as shown above with constant speed. The string makes an angle theta with the vertical, and T is the magnitude of the tension on the string. Express your answers in the following terms of the given quantities and fundamental constants. On the figure below, draw and label vectors to represent all the forces acting on the ball when it is positioned shown in the diagram. The lengths of the vector should be consistent with the relative magnitude of the forces. Okay, so this ball, almost always, unless it's not on Earth, you have gravity. Gravity always goes straight down. So let's see, did they give us mg? And then we have tension here. Okay, it's pointing up in that direction. Any other forces? Nope. Those are the only things pushing and pulling on the ball. Gravity and the tension on this rope. Okay. Now, the next step typically is to do do the net force equations. So net force equals ma. Now, we want to do these in the x and the y direction separately. So I'm going to do y direction first. We're going to say this is positive y direction, this is positive x direction. Okay, so in the y direction, my net force is, gravity is up and down, it's in the negative direction, but the tension actually has two components, force in the x and in the y direction. And given this is theta, what we want to say, the y direction is cosine, it's t cosine theta. It's the adjacent side, because this is the hypotenuse of this right triangle. T, the cosine of theta, is adjacent over it. So the magnitude of this, so net force minus mg, because mg is in the negative y direction. So I'm going to add these two together. That has to equal ma in the y direction. But because this thing's rotating in the x plane, like here, going around in a circle, it actually has no y velocity, y acceleration. So this is 0 because ay is 0. So therefore, t cosine theta equals mg. And I can solve for m. M is equal to t cosine theta over g. And this is an acceptable answer because we're given t, we're given theta, and all of that. So I've solved for mass in terms of those constants. Determine the speed of the ball. For the speed of the ball, I have to look at the x direction. So let's look at the x direction net force equation. In the x direction, it has a force, it only has a single force component. It has t sine theta. And that has to equal ma in the x direction. Now, the mass of it, the acceleration in the x direction is centripetal acceleration, right? It's feeling a force directed towards the center, and it's going in a circle. So this is v squared over r, where r in this case would be the length. R is the, what is r? R is the radius of the circle that it's going, right? This is r. To find r, I have to use a little bit of trig. I know that sine of theta is r over L, so sine theta equals r over L. So that means r is equal to L sine theta. So when I do this equation, I have t sine theta equals m v squared over L sine theta. Yeah, that's it. Okay, now I can solve for v. I multiply that, I get t L sine squared theta over m is equal to v squared. Now, I can't put it in terms of m. They weren't given m, but I solved for m there, so I can plug m into the mass into here. So I get TL sine squared theta over t cosine theta over g. That's v squared. So v is equal to the square root of this. The t's cancel. G goes to the numerator. So I do gl sine squared theta over cosine theta. Okay. Determine the frequency of revolution of the ball. The way I do frequency is it's 1 over period. F's equal 1 over period. The period is equal to you can use some of the angular acceleration equations. I just kind of reason out what the period is. The period is the time it takes to travel here. If it's I know it's velocity times time. Velocity times its period will be the distance it's traveled, which is 2 pi r. So so I can solve for t. T is equal to 2 pi r over v. So that means f, which is 1 over t, is equal to v over 2 pi r. We know what v is, and we know what r is, so this is 1 over 2 pi. For v, I'm going to do the square root of all of this, gl sine squared theta over cosine theta. And then r, we decided was L sine theta. Now, I can actually technically simplify this. You could leave it like this, but this sine squared, I could factor it out. It would be sine theta. It actually cancels with this. So to be fully complete, I would say f is equal to 1 over 2 pi. Let's see, the square root of L over L brings L to the number. So it would be g over L cosine theta, if you wanted to really simplify it. This answer would have been fine, but this is just a little bit of algebra to simplify it. Okay, suppose the string breaks as the ball swings in its circular path. Qualitatively describe the trajectory of the ball after the string breaks, but before it hits the ground. Well, it will just travel tangentially. I'll just kind of sketch it. It kind of goes like that. Because once you cut it, it will just go on, because it has its at any moment in time its instantaneous velocity is tangential. It will just simply take a parabolic arc to the ground like that. Okay, and that's it. Hope you found it helpful. I'll see you guys in the next video. Thanks for watching the video, guys. Please leave a comment, like, or subscribe below to catch up more of the content, and see any links below. I offer free homework help on Twitch and Discord. See you guys in the next video.